Hello, this is Alex Lamb. Today I'm talking to Zinan Lin from CMU and Sewoong O from UIUC. And we're going to be talking about their recent work on the PacGAN, as well as machine learning in general. So to start things off, can I ask both of you to talk a little bit about your background and what you've been working on?
Yeah, sure. So my name is Zinan. I'm now a first-year PhD student in Carnegie Mellon, and I'm advised by Julia Fenty and Meyer Saker here. And the current work I'm mainly working on is the generative adversarial networks and also its applications.
I see. Sewoong?
Right. Hi, my name is Sewoong. I'm at Illinois. I'm a faculty here. One of the main focus now is in GANs, but I've worked on various problems, including matrix completion, ranking, crowdsourcing, differential privacy, and various aspects of theoretical machine learning.
I see. Is there anything that connects those things in your mind, or is there anything that caused you to shift your interests?
Right. So the main tools that we use in the proof for PacGAN,
yeah,
are derived from things that we used and then developed as a proof technique for differential privacy.
I see.
I'll talk about that a little in the paper.
Yeah.
But the connection is very, very deep and very strong.
I see. What's the research culture like at UIUC, or what are the labs and stuff like?
Mm-hmm. Well, I guess it's similar everywhere because we do theoretical work for machine learning, so we don't need much. So it's just the people and computer.
Yeah.
So I think it's similar everywhere. When I was PhD student at Stanford or postdoc at MIT or here at Illinois as a faculty, I think they're all similar. I could be doing the same research any one of those places. And I'm sure similar as CMU is Zinan. Mm-hmm.
I see. Of the papers that have come out in machine learning, like over, say, just recently or over the last few years, are there any that you're particularly excited about, or any directions you find particularly interesting?
There are too many papers to keep up with. A lot of interesting papers. Well, I'm typically interested in the particular problems that I work on at that point in time. So right now, that's GANs, and there are a lot of interesting papers in GANs.
Yeah.
So some well, Zinan, which one did you find interesting? Which one have you read together?
Yeah, so basically I think the GAN I mean the earliest GAN paper itself is very interesting because GAN idea is very powerful and has can generate very powerful like realistic images, and like the following up papers like the equilibrium and the generalization of GANs, and like there are many like theoretical approach to analyze GAN, and those kind of papers are also very interesting.
Right. So on the empirical side, the progressively growing GAN by NVIDIA, Karas et al.
Yeah.
But I guess everyone who works on GAN knows it. But if I show those images to anyone who's not working, who's never seen GAN, it fascinates them too. So I think that's amazing that they could pull it off.
One of the things I find really interesting about this progressively growing GAN paper is, for a long time in deep learning, it was very hard to get a deep network to train. And there was a lot of interest in this idea that you're going to start with a relatively shallow model and you're going to add layers as you train. Like you have the the pre-training and then the fine-tuning, and there's the deep belief net where you progressively add layers. But I think it's interesting that this works well, and maybe one of the key differences between this and some of the other methods is with this, when you're training with your shallower network, you've also simplified the task that you're trying to solve, because you're only trying to generate these low resolution images. And as you're adding layers, you're also making the network solve a harder task. So if there's a way to generalize that concept, it could be pretty interesting.
Right. If you could take that and then have a framework which could be used and applied for any domain, because progressive GAN is in some sense a little bit specific to images, because you're creating low resolution images. If you could take that idea and apply it in general to any samples in any domain, be amazing. So if you can do it for any data, any GAN.
Yeah. So I guess moving on to your specific research with the PacGAN, can you guys briefly describe what the PacGAN idea is in this paper?
Sure. So like the problem PacGAN tries to solve is called mode collapse. So mode collapse means that the generator is not covering all the modes in training data. For example, if we ask the GANs to learn images of animals, includes dogs, and finally the generated distribution does not include dogs. So this is kind of mode collapse. Yeah. So and the architecture of our PacGAN is actually very simple. So in the normal discriminator, each time you just feed it with one sample, either real or fake. But in, for example, PacGAN 2, each time you feed either 2 real samples or 2 fake samples to the discriminator. And so the only thing we need to change is to double the size of the input layer of the discriminator. And so actually the intuition behind our PacGAN approach is that detecting diversity or lack of diversity is much easier if the discriminator can see multiple samples instead of single sample each time. And we also find some theory behind it to support our approach. And those theory is also interesting.
So I have some intuition that PacGAN could improve results by allowing the network to directly identify either complete mode collapse or partial mode collapse. For example, if one part of the image is getting duplicated in a bunch of samples, if you're taking 2 samples at a time, it would be easier to identify this. But it seems like it could also potentially make your real and your fake distribution more cleanly separated, which maybe could make the discriminator saturation problem or the issue of the real and fake manifolds not overlapping early in training worse. So,
So in the experiments we run, it seems like this the saturation problem you mentioned does not happen. But if packing does encourage this behavior, then we think it seems to be like a orthogonal problem and should be addressed by other means such as regularization, for instance.
If it were to happen, though, maybe it would suggest that something like the WGAN, which targets the case where the 2 manifolds don't overlap, might provide bigger improvements than in the non-PacGAN case, but that's just my guess.
Yeah, so that's an interesting question. So if we use Wasserstein with L1 distance, which is usually used in WGAN, then theoretically there is no GAN for packing because Wasserstein distance with L1 distance is preserved over packing. But if we use like something else like Wasserstein with L2 distance, then there is evidence that packing will help. So actually, we checked the what's the thing with L2 distance with the toy example we have in our paper by looking at how what's the thing distance evolves as we pack more and more samples.
Yeah.
And it has similar packing gain as total variation distance.
You say you see a similar benefit from PacGAN.
Yeah, just in toy example, we didn't do experiments on like real images, but for what's the thing with L2 distance, then it has packing gain.
I see. Overall, just in general, what do you think are the most interesting approaches out there for improving GAN stability?
Yeah, so it is a very open question, and there are many interesting works. So some of the interesting approaches, including like changing the optimization problem itself, such as trying new loss functions or changing the update rule. And examples include like during gains, which changes the min-max gain to just a maximization problem, or on-road gains, or what's the thing gains, or on the methods that add regularization. And yeah.
Oh, wait, what did you say turned it from a min-max problem into just a maximization problem?
Yeah, so it was the during gains paper. So
yeah.
So I guess I read the paper more closely. So one of the lines of research that improves stability of GAN that are interesting are the following lines, where the premise is that because we're solving min-max and not to the full optimality, but we're starting either earlier or using some other means. So that's the causing instability of GANs.
Yeah.
And to attack that, there is a new line of research. For example, dueling GAN paper in NIPS 2017 by Alex Schwing and other people. They address it by turning the inner problem and look at the dual of the inner problem. So instead of min-max, it'll be, for example, min-min, for example, making it more stable to train. Because if you have min-min, and if you stop it, you are getting on upper bound in the minimization, and you're minimizing on upper bound, which makes sense. So opposed to if you have min-max, and if you stop in the between, you're getting a lower bound in the inner problem and minimizing a lower bound, which is less stable. So those seem to be promising. And another one along the line, very recent work by Jimmy Ba and Jason Lee. Paper. I forgot the title. It's about drawing some techniques from maybe reinforcement learning to turn the minimax optimization into a more stable form by adding regularization and other things. And those are the kind of research that we find very interesting.
I see. Yeah, it's interesting. In what I've seen, the whole thing with applying like a gradient penalty seems pretty good for improving stability. I haven't seen anyone apply that to like reinforcement learning or
right. Yeah. So I guess it's left open what gradient penalty actually means. Probably it's related to generalization of what discriminator is computing.
Yeah.
Whatever loss you see in the training is also seen at the testing. In this case, testing is when you're training the generator, right? That's when you're testing the loss. So we want those to be similar. So in that sense, I think regularization is very important.
Yeah.
Which regularization is up for, I think, up for debate.
Yeah.
Stability, I think if you're just concerned with stability, one of the main challenge will be how do you show stability? Is there a good benchmark data set where it's hard to stabilize, or maybe there's a way to quantify how stable your approach is in a fair way? It'll be nice. What we see is that for mode collapse, there are some data sets people introduced, so we can measure it, and that's what we use. For stability, I think it's harder. Each paper seems to have its own way of evaluating stability for their method, and all of them are quite interesting ways, but there's no one standard benchmark for testing which idea for stability is maybe working better.
Yeah.
Or more effective.
Yeah, I guess what I tend to see as somewhat convincing for stability is if someone can take a type of architecture that was kind of known to not be stable, like if you do like fully connected nets with no batch norm and stuff.
Exactly.
But it's not quantitative, so. So another thing with the PacGAN is, have you thought about the relationship to Kramer-GAN, which shares the idea of using two samples during training together, but instead what they do is they try to push the two generated samples, especially in a conditional generation case, away from each other in the learned embedding space.
Exactly. Right. So, so Kramer-GAN can be thought of as one way of doing MMD GANs, right? Or kernel mean embedding methods. Which but at the high level, if you want to step back even further, it goes to two-sample testing.
Yeah.
Part of GAN is two-sample testing. Whatever you want to do, or whatever means you have for doing two-sample testing, you could have used it with GAN, and it should do something. And the question is, which idea to bring from decades of studies and in two-sample testing that would work better for GAN, and that's up for I guess us, the community, to make the connection. And one successful line of research is MMD GANs, and at the latest might be Kramer-GAN. And so how is it connect to PacGAN is the following. At the very low level, perhaps that's easier to talk about, how many samples is a discriminator able to take as an input?
Yeah.
Typical MMD GANs, including Kramer-GAN, allows pairwise because they're using kernels, which is based on two samples that's computed about distance, and use it into two-sample testing. So it's connected through the loss also. That's also a big innovation there. But if you, for now, forget about what the losses are, then their discriminator is two samples. Okay, and they could both they compute something for both coming from real data, both coming from the fake data, or one from real and fake, and they're computed in a particular way or connected in the loss. Okay, so in that sense, their discriminators is two samples too per function. It's a function of two input samples, and in that sense, there might be some packing gain, as we call it. So that's the connection, I think, which you're seeing. But fundamentally, there might be some mathematical connection at the higher level. So at the lower level, there are connections in the sense that their discriminator is allowed to see two samples. Our discriminator, we are posing to see two or multiple samples. In that sense, they're related. The high level is the idea of two-sample testing using kernel mean embedding related to the kind of analysis we do on the product space of distributions. That we haven't made a connection precise yet, and that's still open.
Yeah, so I don't know if you guys have had this experience at all, but I remember when the PacGAN paper came out, I read through it and I shared it with a number of colleagues, and it wasn't just one person, it was a few people.
Thank you.
What? Oh,
thank you for sharing.
Well, wait until the next part. But a number of people said that they thought it was the same idea as the Kramer-GAN.
Oh, sure.
And then I thought, like, oh, okay, maybe that's what it is. but I read through both of them in more detail, and they're really different. But maybe if you just look at the abstract, you might think that.
Right. So the idea of showing multiple samples to the discriminator goes all the way back to, I think, original GAN paper, or the next one, improved, training of GAN, has been mini batch
discrimination.
Yeah, mini batch discrimination. And there's a nice paper by Stephanie Jegelka at MIT and Swiss Ra.
Yeah.
Posing similar idea, distributional GANs. The idea is so simple that anyone, it probably has been tried out many times. And some part of oh
no, but I think they're really different.
Right. Some part of motivating like MMD GAN is related to perhaps two-sample testing based on the distribution itself. So we're not claiming we're the first one to do it at all. We're probably the later side, the last one to propose it. But I think the main contribution, if you will, with the way we understand the whole thing through the theorems and toy examples, and the way we test out the idea by simplifying our architecture so that we're only testing the idea of showing multiple samples at the discriminator and nothing else.
Yeah.
Whereas all the other approaches will have other things added on top of it, so that the gains they see or the gains they show will be an effect of multiple things joined together. Okay.
Right.
So in that sense, that's how we're different. And main technical contribution of our thing would be, other than the architecture, I think, but that's simpler and it's related to other things that people have been proposed. We don't deny that. But the way you understand it, the theorems and the analysis, and then that clarifies what packing is doing exactly, is the main contribution. So I wouldn't be surprised if someone comes up and says, well, this idea of packing or showing multiple samples so that you look at distributions has been around before us. That is completely true, and we don't try to sell it any other way.
I see.
But specifically, is Kramer GAN doing what PacGAN is doing? That's different, because not necessarily one is better than the other, one is newer than the other. It's just that they're doing different things. They're motivated by some part. What motivates PacGAN is clear. It's just showing multiple samples as the discriminator, and that's it. Keep everything else the same. Whereas all the other ideas like Kramer GAN or distributional GAN and other things have a little bit of different things tied into it. Like Kramer GAN will be doing kernel methods. That already is different. So how do you compare that with other things? Well, some of the gains they see might come from packing idea, but some of it might come from the fact that they're using the good kernels and they're learning it.
Yeah.
So in that sense, you can think of our paper as simplest paper that's doing what everyone thought about. On top of that, we're doing a very clean theory, and that's what sets us apart.
Yeah.
I can't trace back to many papers which try to do like mini batch discriminator in one way or the other.
Yeah.
And that's fine. I think that has been worked out great.
So one thing I think is interesting is, do you think that the PacGAN would help in the conditional generation case?
Mm-hmm.
Or is there a particular way to use PacGAN in the conditional generation case?
Mm-hmm. Zinan, have we tried any conditional?
No, we haven't.
I guess we have not yet.
Yeah, we have not.
Mm-hmm.
Yeah. Well,
how would you do it if you want to do it?
Right. But it's also a little bit interesting to think about, because let's see. So the thing is, for
the discriminator sees the labels too, right?
Oh, well, it could be a label, but it could be any other kind of condition.
Right, whatever.
Left side, right side.
Sure.
but I guess what's a little bit interesting to me is in terms of the motivation of detecting mode collapse, it would be most interesting, or it seems like it would have the most benefit if you could pack two samples where the conditioning information is the same. Now, for an arbitrary distribution, that's not going to be possible, but depending on what the distribution is, it might be possible. Does that make sense?
So if you have a small number of classes, like 10 or 100,
yeah,
I think it's perfectly doable. You take your favorite conditional GAN, and then show two samples from the class, and that will work better.
Yeah.
Well, if it's not like it's not discrete, for example, if it's a continuous value that you're seeing, like regression type of thing, it's trickier.
Yeah.
Would mixing two from different, for example, classes or something that's far away help you in this way or not? That's I think that's an interesting question. We have never thought about it that way. Meaning which ones to pack, right? How do you pack?
Right, yeah.
We haven't thought about it, but it's an interesting, I think, research direction to come up with the right way of packing.
Right.
For conditional GAN.
Right. So one thing is, have you in the paper you have this this mixture of Gaussians, or I don't know if they're technically Gaussians, they're just like little dots. You have that experiment, and then you have these stacked MNIST digits. And stacked MNIST digits is like multiple MNIST digits are like stacked on top of each other with different colors.
Yes.
Yeah.
So have you tried like other image data sets? And one of the things that could be kind of nice about that is if you did CFAR, for example, you could compute like this this inception score or this Frichet inception distance.
Yeah, so actually we have also evaluate the sample diversity on Salabay dataset. So Salabay, yeah. So basically,
the new manuscript that's not on archive yet. It's ready, but we didn't have time to clean it up. So that'll be the second version that we'll put on archive soon.
Yeah.
Not on the version and that's on archive. The first version that doesn't include this particular experiment.
The Salabay thing.
For example, yeah.
Right. What metric did you use to evaluate on Salabay?
Yeah, so basically we use the same approach proposed in Arola's paper to GANs actually learn the distribution and empirical study that paper. So for each GAN architecture, we select the 20 closed pairs of images according to the Euclidean distance in pixel space and ask humans to tell if any of them are duplicates.
Right.
Yeah.
Is that like the Sanjeev Arora birthday problem paper?
Yeah.
Birthday products.
Yeah.
Yeah.
So there they propose a way to measure mode collapse for any data sets.
Yeah.
And we use that their exactly their algorithm and their evaluation technique.
Yeah. I see.
Yeah. So what we did is that we do that experiment for DCGAN and PacDCGAN too, and for 4 different discriminator sizes. And the result is that in all those 4 sizes, PacDCGAN2 has less probability of collision, which means packing also improves sample diversity on Salabay dataset. Yeah.
I see. I mean, it is interesting when you think about like mode collapse and improving diversity. I feel like even like the really standard inception score should show improvements with that potentially. I guess the Inception score also takes things like fidelity into account in terms of like how confident the classifier is. So maybe the metric you're talking about is a closer fit for detecting mode collapse.
Yeah.
So Inception score is not necessarily measuring mode collapse, because if you reproduce the training data, let's say, or subset of it,
Yeah.
you get perfect Inception score or high Inception score.
Yeah.
Although GAN doesn't do that, so it's not clear if Inception score, how it correlates with mode collapse.
Right.
Although better samples tend to get better Inception scores empirically.
Right.
So that part is, I think, left for discussion. And
I see.
we don't know. We haven't tried extensively yet on like Cypher 10 and Inception score to show one way or the other. But I guess that requires hacking the right architecture, we believe.
Yeah.
So you can pick any architecture, right? Give me, I don't know, spectral normalized GAN or Weissenstein GAN. You could pack it. But I think with Inception score, you have to be careful about which architecture we pack to see exactly what's happening. And we didn't have time to do that yet.
I see.
Mm-hmm.
Yeah. Another thing I'm curious about is, have you studied if the PacGAN makes the training objective for the GAN more stationary? And one like simple test of this would be if it's possible to use like an atom or momentum with a stronger momentum parameter, like 0.9 or 0.99.
Mm-hmm.
Yeah, so we haven't noticed significant improvement in stability, and that actually we didn't try, we didn't really test it yet.
Yeah.
So yeah, maybe.
So it could be related, because maybe the images you're seeing in the end are more realistic.
Yeah.
It could happen that along the way it's more stable.
Yeah.
But we haven't done like extensive experiment to test that yet. But I guess, yeah, in the ones where we've tried, we don't necessarily see more stable training yet, right?
Yeah.
I see. One thing I'm also curious about, which is related to that, is have you studied the types of features that are learned by the PacGAN? So, like what types of pairs of things does it look for? Like, does it just look to see if two things are similar, or are there other types of relations that it could pick up on?
Yes, that's an interesting question, and we haven't done this experiment yet.
Yeah.
I guess so far we were less interested in what the discriminator is learning and more interested in what the generator is learning.
Yeah.
So one line of research that we're very excited about is trying to interpret what a generator is learning.
Yeah.
A good generator. But we didn't do anything about the discriminator so far. For some reason, we're not that curious about what the discriminator is learning. But now that you bring it up, it is actually interesting to compare the discriminator for the packed one and the non-packed one.
Yeah. Yeah.
The thing is that discriminator kind of moves around during training depending on what the generator does, whereas generator goes to one space, right?
Yeah.
The discriminator is generator dependent.
Yeah.
We didn't think we would be reading much because it's going to be changing over the training epochs.
Right. Because it's so relative, you'd have to be careful about exactly how you analyze that.
Exactly.
Yeah, so I don't necessarily have exactly the right experiment in mind, but that would be one thing that I'd be curious about, is like,
right, did it learn something that's different on two images,
yeah,
a point, and try to make sense of it? Or
yeah,
that is a good, actually, good experiment.
yeah.
Mm-hmm.
Well, when answering that question, you said that you were interested in research on analyzing what kind of stuff the generator has learned, or maybe you just meant it in the context of this paper. But is there anything in that space that you're particularly interested in?
Well, at the high level currently, because if you think about the generator that's learned by things like progressively growing GAN, then that function, the generator from 500 dimensions to 1 million dimension, is amazing. It's learned something very, very specific to faces.
Yeah.
So then can we go into the learned weights and then the function and try to understand something about the faces that are fundamental, that without human intervention, so that we could maybe do it for other domains too. You could train it on some, I don't know, some astrophysical signals and then find some patterns, or speeches, and then do other things. It's at a high level now, nothing concrete. But the idea would be that the generators are learning something very, very important and fundamental. Could we figure out what the important and fundamental things are that they're learning?
I see what you're saying. So you're saying the generator learns what kind of manifold the data lies on, but
Right.
is there a way that we can like extract more like analysis of what it's learned about the manifold from the generator versus just having a sampling function?
Yeah, it's at the high level idea that we have.
Yeah.
We have concrete research.
Yeah. I mean, even just having access to, an estimate of the density would be pretty interesting. But
that will be interesting and also challenging, I guess.
Yeah, yeah. Yeah, there could be a number of things in that space that would be cool. So moving on to more details of the paper, could you explain the theoretical approach of PacGAN in terms of hypothesis testing regions?
Yeah, sure. So to explain the connection between our approach and the hypothesis testing region, we may need to start by talking about our definition of mode collapse. So we say a target distribution P and a generated distribution Q exhibit mode collapse if there exists a set where P has a lot of mass but Q has very little mass.
Right.
And yeah, and we show that so we can plot all the possibility, like the possibility of mode collapse into a region which we'll call the mode collapse region, and we show that this region is actually equivalent to the hypothesis testing region, where the null hypothesis denotes the sample being drawn from the generated distribution Q, and the alternate hypothesis denotes the sample being drawn from the true distribution P. So
hold on. If we could go into the definition a little bit more there. Because both are probability distributions and they have to integrate to one, if the two distributions aren't exactly the same, if there's a place where P is lower than Q, or it has a lower density than Q, it means there should be somewhere where P has a higher density than Q, right? So those two have to happen together. So if you define mode collapse by like P being less than Q, or no, sorry, Q being less than P at certain points, does that mean that any distribution that you estimate has mode collapse under that definition, or did I misinterpret it?
I see. So So we don't define mode collapse as a binary like that, but it's by two scalar real values. We call it epsilon delta mode collapse.
Yeah.
So we say target distribution P and then the generated distribution Q.
Yeah.
Get epsilon delta mode collapse if there's some region that P of S is bigger than delta for some set S, but P of S is less than epsilon.
Yeah.
For a given distribution, for particular value of epsilon and delta, it might have the mode collapse or not.
I see. And is epsilon your threshold for the difference between?
Right, you can think of these two as a threshold. Delta on the P side, epsilon as a Q side.
Yeah.
And if P has bigger than the threshold delta and Q has less than the threshold epsilon,
I see.
Different choices of epsilon and delta, then you see we say that the distribution pair P and Q have epsilon delta mode collapse.
I see.
So if P and Q are the same, then it will only have epsilon delta mode collapse for epsilon equal to delta.
Right. So the idea then, I guess, is that you know, depending on what the epsilon or delta are, if the value of your estimate, I guess, stays above the epsilon everywhere, you could have a lot of estimation error, but still not have mode collapse. If I use the right term.
Right. So what is the estimation error here? What are you estimating?
Let's see. Police are coming for you.
Sorry.
That's okay. So epsilon is the threshold for P, right? Or is epsilon the threshold?
Delta was for P, epsilon is for Q.
Okay.
So larger delta, smaller epsilon means more mode collapse.
I see. I guess all I was saying is you can have estimator distributions there where you don't have mode collapse, but you do have estimation error as long as it stays within those thresholds.
Right. So this is a definition at the population level. And if you have finite sample estimators, then the estimation error should be on top of these two.
Okay. So I guess I could let you continue, or could you talk more about, like, I guess, how that relates to hypothesis testing?
Yeah, sure. Yeah, so we make a connection between hypothesis testing region and mode collapse region. So basically, we can show that they are the same thing.
Yeah.
So after that, we can bring the powerful results from hypothesis testing region into our problem.
Right.
So for example, the total variation distance between the two distributions is closely tied to the shape of the hypothesis testing region, or the mode collapse region. And the shape of the mode collapse region is closely tied to the amount of mode collapse you have. So by looking at how the shape of the mode collapse region evolves as we pack more and more samples, we can get bounds on the total variation distance between the productly generated distribution and the product real distribution.
Right. Can you explain, like, what the idea of hypothesis testing is at a high level? Like especially if people are less familiar with statistics, or that subfield of it, I guess.
Yeah, sure. So in the hypothesis testing, we use the so there are two hypotheses. The null hypothesis denotes that the sample being drawn from the generated distribution Q.
I see.
And the alternate hypothesis denotes the sample being drawn from the true distribution P.
Yeah.
And given a sample from the experiment, we can make decision on whether the sample comes from P or Q based on the rejection region. So it means that if the sample is in our rejection region, then we reject the null hypothesis.
Is the
Okay.
is the analogy with hypothesis testing and statistics like if I'm doing like if I'm a social scientist or some kind of experimenter and I draw like a sample of like 30 people, I want to figure out like when I can reject the null hypothesis, and that like 30 people in the experiment is analogous to the number of input data points that you're packing as inputs to the PacGAN. Does that make sense?
Yeah. So yeah, I think it is the similar hypothesis testing. So we basically we have a sample and then we make decision whether it is A or B, something like that.
Yeah.
Yeah.
Oh,
Okay.
can you explain what type 1 and type 2 errors are in hypothesis testing and how it relates to the PacGAN?
Yeah. So type 1 error in our case means that the null hypothesis is true, means that the sample was generated, but we rejected, which means we thought it was real.
Yeah.
And type 2 error means that the null hypothesis is false, which means the sample was real, but we accept it, which means we think it is fake.
Yeah.
Yeah. It is the type 1 error and type 2 error in our case. And we can draw the convex Hull of all achievable type 1 error 1 minus type 2 error pairs as a region.
Right.
And it is the hypothesis testing region. And
Okay.
and it is exactly equivalent to the mode collapse region we defined. So
I see.
yeah, so basically, given a point epsilon delta in our mode collapse region, we can map it to the hypothesis testing region where the epsilon corresponds to the type 1 error, and the delta corresponds to 1 minus type 2 error.
Okay.
Yeah, so this is the connection between those two regions.
I see. Do you think for just like, I guess, generative models more generally, what kinds of theory from like this hypothesis testing literature, or like what value do you think it could bring to the generative modeling research? If that makes sense.
So you mean what theoretical tools can we bring from hypothesis testing for researching maybe adversarial training?
Yeah, or for generative models in general, but yes.
Right. So the connection is that because we're using adversarial training, we are creating using neural network that performs hypothesis testing. So the connection is fundamentally there for any GAN.
Yeah.
What theory would help you is not clear. You need to be more creative and innovative. In this particular PacGAN setting, we were able to make the connection to come up with a proof technique.
Yeah.
Definition of mode collapse, which allows to show that this idea of packing is fundamentally related to mode collapse as we define it.
I see.
The strength of mode collapse is fundamentally connected to our idea of packing.
Yeah.
And that's the main contribution of our paper.
Yeah.
What other techniques might be relevant? So there are a few other problems that we're tackling right now using hypothesis testing ideas and proof techniques from like information theory and or statistics.
Yeah.
Which we believe there are. So I guess where we are at is we believe there are a lot of things we could bring from hypothesis testing.
Yeah.
To say something that we don't know about GANs.
Yeah.
Well, which one specific needs personal manual going and digging and understanding. So I think our paper is a good place to start for anyone because it has fundamental theorems and math from hypothesis testing telling something very specific about training GANs.
Yeah.
That could kind of be a motivation or inspiration for other people. What else is there? We're looking right now.
Okay.
We'll see. Maybe our next paper will be along making that connection for other type of questions in GAN. with other type of tools in hypothesis testing.
I see. One thing that I've been curious about for a while is, for a while with the GAN research community, there's been an idea that maybe there's a trade-off between mode collapse and sample quality. So the idea was maybe you can learn a generative model which goes further in the direction of having high sample quality, at the cost of being less representative. And I mean, it's definitely true that at least conceptually, this kind of a trade-off could exist. And even if you draw like simple examples, like you say, okay, my true distribution is a mixture of separated Gaussians, and my estimator distribution is just like a single Gaussian, I kind of have a choice between fitting one of the modes really well or trying to
or having that really wide Gaussian that kind of covers, and that's
yeah.
I see the point.
What I'm curious about is, do you think that this is like actually like an important issue with GANs, or like a central problem with generative models? Or do you feel like it's maybe not?
Is there a fundamental trade-off that we cannot maybe overcome? Meaning, if we want diversity, maybe we have to lose on accuracy. So far, experimentally, it's the other way. So whenever we get more diverse outputs using either PacGAN or other things that we experiment with, we get better samples. Individual samples also better.
Yeah.
So we don't know if there's such a fundamental trade-off exists or not.
Yeah.
Current techniques that we haven't met the barrier of the fundamental trade-off, even if there is one. So right now you can improve on both. That's what you see in like all the great GANs that the community has come up with. Although all of those, I think, improve both sample quality and the diversity.
That seems pretty
too far. Are we gonna hit the barrier or not? That we don't know, and we don't know even. There's no either theoretical and experimental indication of that.
Yeah,
it doesn't mean otherwise either. So we're not there yet.
I see. That seems to fit with my experience, where a lot of times if you have pretty bad mode collapse, it tends to make the training
harder,
unstable, and it also tends to hurt.
We see that all the time.
What'd you say?
We see that all the time. The ones that are really, really hard to train or really unstable, the ones that have mode collapse and just doesn't get out of that mode collapse.
Yeah. So in terms of this area of like mode collapse research, or I guess for any kind of machine learning, if there's someone who's looking to get into it or is looking to contribute, is there any advice you'd have for them, or anything you suggest they work on or look into?
This is a very hard question. So many good ideas are being discussed over many like medium, like blogs and like interviews like we're doing here, or YouTube and other things. So I think if someone's trying to get, well, let's say someone who has training in some area of like statistics or theoretical understanding of machine learning, or some other relevant domains, but are thinking of doing something in machine learning. I think one way to do it would be to try to follow the latest. And there are many like Reddit and there are Twitter and a lot of things. It can be overwhelming. That's, I think that's where the latest things are being discussed, and that's how we discover a lot of interesting new papers and ideas on GAN. And like open review system at ICLR provides not just the papers, but also all the comments and reviews and discussions. But those are overwhelming. There are just too many. But if you can find something that's perhaps a connection to what you know and what you do, whether it's optimization or control theory or any part of, learning theory. Try to follow what's latest that uses those techniques in machine learning. And I think you can maybe get some idea of what's interesting and what's important.
I see.
Mm-hmm. That's
all right.
One way, but machine learning and deep learning is such a big area now with so many people with so many interesting papers. So you have to find one that fits you, I guess.
I see.
Mm-hmm.
Well, it was great having you guys. I really appreciate it.
Thank you for having us. It was great.
Yeah, thank you very much.
All right. Have a good day.
All right. Thanks. Bye.
Thanks. Bye.